Grasp Optimized Motion Planning, GOMP, aims to speed up repeated pick-and-place motions and, by extension, increase the rate of picks per hour. Improving automation productivity is increasingly important due to the demands and worker safety issues created by the ongoing pandemic. Due to recent advances in image and grasp analysis, the robot's physical motion is becoming the bottleneck in pick-and-place operation. We consider the pick-and-place operation in which a robot manipulator arm picks up an object from one bin and places them into another. To speed up motions, we want fast, smooth trajectories that are constrained by grasp analysis, avoid obstacles such as the bin wall, and operate within the robot's physical limits. Grasp-optimized motion planning takes as input a grasp analysis. For example, given a mug, grasp analysis will generate a pair of contact points for a parallel jaw gripper. In traditional pick-and-place environments, the robot gripper would make a top-down grasp to pick up the object. GOMP instead views the pair of contact points as a rotational degree of freedom. This degree of freedom allows the motion planning optimizer to select a grasp angle that leads to a faster motion. We use grasp analysis provided by DexNet to generate the grasp contact points and add a continuous degree of freedom to the optimization. Other grasp planning approaches could also be integrated into GOMP, and many have explored generating grasp with additional degrees of freedom, though have not integrated it into an optimizing motion planner. Motion planning between multiple starts and end points is readily handled by many sampling-based motion planners, including asymptotically optimal ones, though sampling-based motion planners will typically require a post-processing step to smooth and optimally time parameterize the motion. One possible approach would be to take the output of a sampling-based motion planner and pass it through a trajectory smoothing and time optimization process. This, however, may not yield a fully time-optimized trajectory, as this process typically computes timings for existing trajectories while not modifying or only heuristically modifying the trajectory. Instead, we propose a process that simultaneously optimizes the trajectory and its time parameterization. Optimizing motion planners, on which this work is based, compute optimized trajectories but typically only consider heuristics such as distance or sum of squared distances traveled between waypoints. Instead, we compute an optimization that directly considers the joint's limits and dynamics. Prior work has also explored integrating motion planning in various forms with grasp analysis, sometimes rapidly switching between the two. In the approach we propose, we integrate the motion planning with a degree of freedom informed by grasp analysis. We formulate the grasp-optimized motion planning objective as follows. GOMP minimizes the time over a sequence of joint configurations, subject to grasp analysis, obstacle avoidance, and joint limits. The grasp analysis degree of freedom, due to robot kinematics, is not a convex constraint. Obstacle avoidance is also non-convex. To compute the trajectory, GOMP uses a sequential convex program modified from Trajop on a trajectory discretized with a fixed time interval between each step. We first walk through how GOMP minimizes a trajectory's sum of squared accelerations. We will then describe how it minimizes trajectory execution time. With a sequential convex program, the joint configuration, velocity, and acceleration constraints are convex. The boundary constraints, namely that it must start and end with zero velocity, are also convex. GOMP uses a model predictive control style constraint on the dynamics of the trajectory to ensure that the trajectory is dynamically feasible and the joint limits are properly constrained. This is also a convex constraint. GOMP handles non-convex constraints from obstacles by linearizing the constraint and establishing truss regions into a sequential convex program. The obstacle constraints are linearized so that trajectories are pushed up out of collision with the depth map. This means, in practice, that arms will always have a direction to move out of collision. Computing the linearization of obstacle constraints requires a Jacobian of the end effector's position. The linearization establishes a convex constraint applied to the joint configuration that will either push the trajectory out of collision or keep it out of collision. In the convex optimization, the linearized obstacles look like this as constraints. GOMP applies a similar approach to the linearization of constraints around grasp pick and placement points. This time, the constraint is bounded so that gripper maintains contact while allowing changes in the degree of freedom implied by the contact points. Putting the entire convex optimization together, GOMP has a quadratic program that can be efficiently solved. However, since the linearization of the non-convex constraints is only valid for a small region, we use the truss region-based sequential convex program from Trajectories to solve this minimization. To expand on how truss regions operate, we show here the configurations of a trajectory after an iteration of the optimization process. GOMP establishes truss regions as linear bounds on the configurations of the trajectory for which the linearization of the non-convex constraints may be valid. If the linearization is invalid, for example, the convex optimization step produces a less optimal result, GOMP shrinks the truss region. Conversely, if the convex optimization improves the result, then GOMP grows the truss region. The specifics of the algorithm are in the paper. With these constraints put together, GOMP produces a smooth trajectory. Here we show plots for the UR5 robot's 6 joints, their configuration, velocity, and acceleration plotted over time. After computing this solution, GOMP then minimizes the trajectory time by incrementally reducing the number of steps along the trajectory, and solving the sequential convex program again. This process may be stopped at any time or repeated until the solver detects that the problem is infeasible. The following animation shows the time minimization process. At this stage, shortening the trajectory by a time step is no longer feasible due to the joint constraints. In physical experiments, the UR5 with a robotique gripper moves an object from a table to a bin. DexNet provides grasp analysis from a top-down depth camera, and GOMP computes the arm trajectories. From the top-down camera, we generate grasp analysis using DexNet. Here we show multiple dispersed candidate grasp points for each of the objects. For any object, GOMP then computes the time-optimized motion for the grasp point. We compute optimized trajectories for each of the candidate grasps in parallel. In experiments, we record and report each of these, but only execute the fastest motion. In practice, one could make a trade-off decision between grasp reliability and trajectory speed. We compare to a baseline motion DexNet uses in practice. This motion sequences a lift, horizontal translation, and lowering at the UR5's maximum speed. Since the motion stops at each direction change, it is slightly slowed. The baseline motion only indirectly avoids obstacles by lifting high enough to avoid any possible collision. In comparison, we see that GOMP trajectories are at worst 5.8 times faster, on average 9 times faster, and up to 16 times faster than baseline. In the mug example, we compare the trajectory times of the 8 grasp points versus the baseline, observing that the fastest motion of 380 milliseconds is 13 times faster than the baseline. GOMP presents many exciting avenues for future work. In experiments, we focused on the UR5 as it is a common robot arm used in warehouse operations. However, it only has 6 joints. To address issues that may be faced by robots with higher degrees of freedom, we planned to run experiments using Fetch 7DOF arm on additional tasks. We also manually integrated DexNet, running grasp analysis in one process, then feeding it into the optimization process of GOMP. We are still developing and improving the motion planner and hope to integrate it into the DexNet pipeline. While we consider adding degrees of freedom to both pick and place points, we have not considered how placement points would affect the subsequent optimization of a motion for the next pick point. This, in a sense, is a traveling salesman problem, which we hope to address using some recent advances in that area. In conclusion, grasp-optimized motion planning uses a progression of sequential convex programs to produce fast, smooth, time-optimized motions that speed up repeated pick-and-place operation. We are actively working on extensions to this project and would welcome ideas for collaborations. We hope you will check out our paper and project website and contact the authors if interested. Thank you.